Hello everyone. Today I want to share a simulation of the impact of honeycomb bugs. As we can see, this is a rigid object as impactor, and this box is a honeycomb structure inside, and I can show you the inside structure. So this is the deformation and the stress distribution. Then let me show you how to create this model and simulation. So this is a part, and how to create this part, I can tell you the steps. First, we need to create a unit of the polyhedron. So this is the unit, and here is the sketch of the honey unit and the dimension here. So we use the extrude tools to create this surface, and then we can make a merge of multi-units, so we can get this one. Before I add the surfaces at the outside, it just as this, and the thickness of the walls are different because we know how the honeycomb made. So this walls is the thickness is 2 times as this one, and I can show you the thickness of the walls. So and the thickness I can show you in this section. So this is a double wall, and this is single wall. So the double wall is 2 millimeter, and the single wall is 1 millimeter. Then the out surface has a thickness of 4 millimeter, or 0.5 millimeter, and the material is aluminum. After we get this honeycomb, then we need to create the outer surface. So first of all, we need to extrude the outside wall. So that's the step here. In the sketch, we create a rectangle as the outside wall and extrude it for 6 millimeter and the same height with the honeycomb. After this, we need to create the top and the bottom surface. This we can create the surface by this tool, Cover Edges. After we created the top surface and bottom surface, then it is a closed box, and inside is the honeycomb structure. So this is the honeycomb box. Then we create the impactor. It is an ellipse, so I need to revolve it to get the shear body. And the long axis is 30 millimeter. After revolved for 360 degrees, then we get the closed surface, and we create it as a discrete rigid. So we need to give it a reference point here. Then to get the uniform measures, we cut it with 3 planes. So we create the 3 datum planes. As we can see, these planes can be created by these tools. So after we cut it to 8 parts, we can get a bed meshes. As we can see. And for this rigid shear body, we can get a structure mesh. And the mesh size is about 1.5 millimeters. Because it is a rigid body, so it needs a mass of this object. So I give it engineering features, inertia. And for this reference point, it has a mass of 0.05 kilograms. It's just almost the mass of an egg. So these are the 2 parts. Then we need to create material. Here we create 2 materials. And the surface is the aluminum density and plastic property. The yield stress is about 120 megapascals. And the second is the honeycomb structure. And they're made of some kind of paper. So its Young's modular is 10 gigapascals, and the Poisson ratio is 0 to 8. The density is 2.6. So after we create these 2 materials, we need to create the sections. Because these are all shear sections, we need to create different section property for different thickness. As we can see, The aluminum has a thickness of 0.5 mm, and the double wall of the honeycomb is 2 mm, and the single wall is 1 mm. These are the three section properties we need to use. Then we need to assign the section to different thickness surfaces. So I can hide this top surface to see the inside thickness. So this is the thickness of the honeycomb structure and the outside walls. The aluminum has thickness 0.5 2 mm, and this is 1 mm. After we assign the section property, we go into the assembly module. In this module, we need to adjust the location of the two parts and make it as the initial position of the simulation. Then we create a dynamic explicit step, and the time period is 2 milliseconds. Because there is a contact in the process of impact, we need to create contact property, and it has a friction coefficient of 0 to 5, and we create a surface-to-surface contact interaction. And the rigid body has a master surface. The top surface as the slave surface. Then in the result, I want to know the contact force or the impact force between the impact. So in that step, I create a history output here. And at the domain, I choose the interaction, and it has the into 1. Here I choose the CFN, the total force due to contact pressure, and the total area in contact, and total forces due to frictional stress. So after we define this history output, we can check the contact force in the result. So in the load module, I need to fix the 4 edges of the box and give the rigid body an initial velocity. So first we fix the 4 edges of the honeycomb box, and second is the rigid object, and we constrain the freedoms except the U3. And we give it an initial velocity And in this case, we give the velocity in the z direction, negative z direction, as 1 millimeter per second. Of course, we need to give this model of gravity here. So then we create the mesh for this honeycomb structure. We give the mesh size of 1 millimeter, and to get a quad shape element. After all of this, we create a job and submit it. It will solve in 20 minutes, about 20 minutes. So I can check this result. Here is the stress, and we can show the animation. As we can see, the alumina in the center part of the top surface has yielded and we can get the contact force curve here, and the max contact force is about 95 newtons here. And we can also create the curve of the displacement or impactor here. This is the reference point of the impactor. So we can also check the energy curves, and the blue curve is the internal energy, and the green curve is for the kinetic energy. So at first, the kinetic energy is about 25, and the internal energy is 0. Then, when the contact happened, the kinetic energy converted to internal energy. Then we can check the contact area. The max contact area is about 27 millimeters square. We can check the displacement. So this is when the impact velocity is about 1 meter per second. Then I copied this model and to change the impact velocity as the velocity when it falls from 1 meter height. So then the initial velocity will be 40.2 meters per second in the negative z direction. And the other conditions are the same. Then we also solve this problem. So here is the result. As we can see, the erosion is larger than before. And we can compare the contact force curve. This is the contact area. We need the force and the force, this one. Oh no, I check the other one. This is the force and the force. So the blue curve is when the initial velocity is about 1 meter per second, and the yellow curve is when the velocity is about 4.2 meters per second. As we can see, when the velocity increases, the response time is shorter, but the contact force is larger. So we can check the number, the value, 535 newtons, and the first one is about 95 newtons. It's about 4 times, 4.5 times. And we can also compare the other curves I have created here. This is the displacement of the reference point of the impactor. So we can guess without doubt the yellow curve is for the first model and the red curve is for the second model, because when the velocity increases, the displacement is get larger, and the value is about 3.8 times of the first model. The first one and the second one, it's about 3 times. Of course, we can check other results if we want. This is the contact press.